Aleksandar, and today I'm talking about FaRM. And FaRM is actually more general than just a key value store. So it's our distributed computing platform for modern data center hardware. Okay? FaRM is motivated by two hardware trends. One is the low cost of main memory, which enables us to build commodity servers with large amounts of main memory. And that in turn means that a small cluster of several tens of machines can already have tens to hundreds of terabytes of DRAM, which is enough to store entire data sets of most applications. And once the data goes to memory and these are not accessed as often, the TCP networking stack actually becomes the bottleneck. So luckily we have these new data center networks that can help alleviate this problem. So basically these are HPC computing networks from several years ago, right, making their ways into data centers. They have really good performance, very high throughput, very low latency. And in addition, they expose these interesting RDMA primitives. RDMA stands for Remote Direct Memory Access. It actually means that a machine can access data in memory of a remote machine directly. Okay? How does this work? I'll show you an example. So here, in an example, we have two machines, machine A and B, and machine A reads some data from memory of machine B. To do so, the CPU on machine A initiates the request, which then gets sent to the NIC on machine B. And machine B, instead of interrupting the CPU, which is what's typically done in message passing programming paradigm that's used today, actually sets up the DMA transfer and directly fetches the data from memory, so without interrupting the CPU. It sends the data back, and the data gets stored in memory of machine A, where it can be used by the program running on machine A. And in FaRM, we actually use RDMA very extensively. So you can think of FaRM as a project which explores how to use RDMA to build distributed systems. Okay? So we use RDMA to directly read data in memory of remote machines, and we also use RDMA writes to implement a very efficient message passing mechanism. Okay? And performance of these networks is really great, as I mentioned several times so far. There are two reasons basically for this. One is that the network bypasses the kernel as the network processing is basically offloaded to the NIC. And the other is that it also bypasses the processing on the remote NIC if we can use RDMA. And here's what I mean by great performance. Here I'm showing results from a micro benchmark. So this is a random read benchmark. We have a cluster of 20 machines connected with 40 gigabit Rocky RDMA network. And each of the machines continuously issues read requests to other machines in the cluster. Each of the requests goes to a randomly selected machine and fetches some data from a randomly selected offset in the exposed memory on that machine. And the transfer, the size of the transfer in the micro benchmark is shown on the x-axis, and the y-axis shows millions of requests, or read requests per second per server. Okay? And we implemented this reading using three different techniques. Either RPC or TCP-based network, so this is basically the line you can see here at the bottom. Then we implemented it using RPC over our efficient RDMA messaging, so this is the red line in the middle. And as you can see, already just replacing the messaging mechanism gives us almost an order of magnitude improvement in throughput. But in addition, if you're able to use RDMA to directly read data in memory of a remote machine, we can get another factor of 2, right? And we are today getting a factor of 2 because our system is bottlenecked on the request rate processing by the network. But in the future, as request rates go up, we expect to become CPU bottleneck. So this gap is actually going to increase. And using RDMA is going to become even more important than it is today. We also measure the latency on the same cluster. And basically, the story is the same. Again, an order of magnitude improvement in the lowest latency that we measured on this system. So these network characteristics are really great for applications running in data centers today. So for instance, applications that have irregular access data patterns and are latency sensitive, like key value stores or graph stores. But we also expect that this kind of network performance is actually going to enable new applications. Okay, so these are basically the settings in which work. And in the paper, we make several contributions. We basically explore how to use RDMA at all levels of the system stack to build distributed systems. In the talk, I'm going to be able to talk only about a few of these things. I'll talk basically about the programming model that FaRM exposes to the applications that enable common use of RDMA primitives. and then I'm going to talk a little bit about how we implement and how we use FaRM. So let me start with the programming model. One of the questions that we asked ourselves when starting with this project was how to program a modern cluster. And by the modern cluster, I mean a cluster with terabytes of DRAM, hundreds of CPU cores, and this very efficient RDMA network. So just to give you an example, the cluster that we use for the evaluation in this paper is a cluster with 20 machines, 2.5 terabytes of DRAM, 300 CPU cores, 320 CPU cores, and this 40 gigabit RDMA Rocky network. Okay? And based on the system characteristics and on the results of our micro benchmarks, we would like to have the applications that keep data in main memory, that access data using RDMA as much as possible, but also we would like to enable local access to memory, right? We would like the applications to use faster local access to local data. And access to local data is actually basically about a factor of 20 faster than access to the remote memory, even when using RDMA. So this is really important. In FaRM, we basically adopt this symmetric model, where applications both store the data and execute the computation. So this is slightly different from a traditional model where a number of servers is used to store and serve the data, like a key value store, and then other machines are actually used to run the application code. Okay, so we go for this symmetric model for two reasons. One is that I already told you, access to local memory is much faster, right? So we would like to be able to collocate the computation and data to exploit this. And the other is that we are actually using RDMA extensively. So servers which serve data using RDMA do not use CPUs a lot. So the server CPUs would actually be underutilized. And in order to use these basically spare CPU cycles, it's very good to put both the data serving and the application code on the same servers. Okay, so what do applications see when they use a FaRM? So basically, FaRM takes the memory of all machines in the cluster and builds a shared address space, where the applications can manipulate objects in this shared address space. And the reason to go for the shared address space is actually, again, our desire to use RDMA as much as possible. So in order to perform an RDMA access, for instance, an RDMA read, you need to know the starting address of the transfer and also the size of the transfer. And this naturally pushes us towards a shared address space model. So this is a different motivation than previous systems that present the distributed system as a shared address space, where the main motivation was basically improvement in programmability. And for us, the main motivation is performance, and programmability benefits are basically a welcome bonus. Okay? So what can applications do in this shared address space? Basically, the main primitive that FaRM exposes are transactions. So these are fully general distributed transactions. And transactions actually mean atomically executing multiple operations in this shared address space. And the operations are reads of objects, writes of objects, allocations, and deallocations of objects. So operations you would expect to see in a shared address space system running on a single machine. Okay? And as I told you, the transactions are very general. We expect the programmers to use transactions to basically implement the majority of the code of their applications, because they can use them to basically write any kind of a complex operation. We go for very strong consistency, so our transactions are strictly serializable. So these are basically ACID transactions. And the reason why they're easy to use is that basically they hide the location of objects, also the concurrency in this very highly concurrent system, and failures. Okay? So we provide fault tolerance as well. So our transactions actually run quite well because we keep the data in memory and have this very fast network. But we also expose two mechanisms to further improve performance of applications. One are lock-free reads. So a lock-free read is an atomic execution of a single read. So the program can read an object, get a consistent state of the object, but there are no guarantees across multiple reads. Okay? And lock-free reads are very efficient. They're implemented with a single RDMA read. They're also strongly consistent, so you can think of lock-free reads as a transaction that consists of a single RDMA read. So they can basically execute at the same time as other distributed transactions execute. Okay? What makes them harder to use is that they're harder to compose. Basically, if the program needs an operation that accesses multiple objects, a strong consistency across multiple reads, this is harder to achieve with lock-free reads and with transactions. Actually, FaRM exposes several mechanisms to enable this custom validation tricks that are needed to use lock-free reads in some cases, and we discuss some of these in the paper. And another way to optimize performance is actually to use locality, so to use local accesses. I already told you local accesses are by a factor of 20 faster than remote accesses. So FaRM enables actually applications to allocate the related objects on the same server. Okay? and then it also enables shipping computation to the server that holds the data. So basically, a server can send an RPC to the server that holds all the data, which then performs all the accesses very efficiently using local accesses, right? And then returns the result. We also optimize the single server transaction. So this further promotes use of these locality-aware optimizations where needed. Okay, so this basically concludes my brief overview of the programming model of FaRM. So we basically have a shared address space with transactions for writing general code, and then log-free reads and locality-aware optimizations for optimizing performance-critical pieces of code. Next, I'll tell you how we implement our transactions in log-free reads. So transactions in FaRM are general, fully distributed transactions. Basically, a transaction is executed by a single server. In this case, this is server S1. And during the execution, the transaction can access objects living anywhere in the cluster. So basically, on any of the machines in the cluster using RDMA reads. Transactions are optimistic, so they buffer all the writes during the execution and apply the updates only at the commit time. To commit a transaction, FaRM uses a two-phase commit protocol for optimistic transactions. So the first step is basically locking the write set, which is done by sending messages to the machines that hold pieces of the write set. Then they locally lock the objects and send the responses back. If the locking succeeds, the server, the coordinator, in this case server S1, basically validates the read set. This is done by using one-sided RDMA reads. So validation basically ensures that nothing that was read during the execution has changed since then. And if the validation succeeds, we can basically, the transaction can commit, and then it applies all the updates. So we send one-way messages basically to update and unlock the objects. And the reason we can send one-way messages is that our network actually exposes in-order reliable transport. Okay? So there are two things I'm not mentioning here. One are these optimizations for transactions that access objects on a single server. And the other thing is that we actually also replicate data here. So we send the data to additional machines, to replicas, which basically log the updates to SSDs. You can think of this as very similar to what's done in RAM Cloud. So this way we actually also achieve fault tolerance. Okay? So this is how we do transactions. Let me next tell you how we actually implement log-free reads. I already told you log-free reads enable the application to read contents of a single object in a consistent manner, and they are implemented with a single RDMA read. So I'll start by telling you how you would implement log-free reads in a traditional setting on a single machine. Okay? To do that, we would put a version in the header of the object, and then use this version to detect basically inconsistencies. During the updater logs the object first, then updates the data, and then unlocks the object and increments the version. The reader first reads the version, then reads the data, and then reads the version again. And if the two values of the version are equal, basically the reader has observed a consistent state of the object and can use it further. Otherwise, it discards the read and basically restarts it. So this is, again, another example of optimistic concurrency control primitive. Just a note here, for this to work, we need to avoid overflows of the header version. For this reason, we use basically 64-bit versions in the header. And this is really a nice way of implementing log-free reads on a single machine system, because we basically avoid locking during reading, which improves performance a lot. But this is not a great way of doing this in our setting for FaRM. And the reason is basically that this would require 3 network accesses. And remember, we are actually shooting for this performance improvement factor of 2. And at least on today's systems, right? And using this approach would actually defeat the purpose of using RDMA for reading. So we need to do something else. And this is how we implement reads in FaRM. So basically, we start from the same starting point, put the version in the header of the object. And then we use the characteristics of our hardware. So our NICs are actually cache coherent. And this means that they observe the updates in the same order in which they are performed by the CPU inside the single cache line. So there are these ordering guarantees inside the cache line, but there are no ordering guarantees across cache lines. So what do? So let's say that in this example we have an object lives in 3 cache lines. So we put a version basically in each of the cache lines. Then when updating the object, we lock all the cache line versions, then update the data, and then unlock and increment the cache line versions. So note that this added complexity during the update is not a significant overhead, because all these accesses are performed locally during the two-phase commit protocol I showed on the previous slides. Okay? And having the cache line versions actually enables us to perform a read with a single RDMA read. So we perform the read, fetch the whole object, and check that the versions match. If they match, we have a consistent state of the object. Otherwise, we have to discard the result and perform additional reads. Okay? So this is how we can implement log-free reads actually with a single RDMA. There's a small problem here with this scheme as described so far. Basically, remember I told you that we have that we are using 64-bit versions, okay? And cache lines are only 64 bytes. So this would mean that we would incur 12.5% of space overhead, which is quite high for a main memory system. So what we do is to improve space efficiency, we actually use 16-bit versions in cache lines. So we use a 64-bit version in the header, and then we use the least significant 16 bits in each of the cache lines. And the reason why we can do this is that we need to avoid cache line version overflows only for the duration of a single RDMA read. Okay? So in addition to checking versions, we also measure how long it takes to perform an RDMA read. And if it takes longer than it would take updaters to actually overflow one of the cache line versions, we then discard the read. Otherwise, we can accept the results. Okay? So let me show you an example. Let's say that for a particular size of the object, the minimum time to update an object is 40 nanoseconds. Okay? That means that the maximum amount of time we can tolerate the RDMA to take is basically 2 milliseconds. So this is 40 nanoseconds times 2 to the power of 16, because we have 16 bits, times 1 minus epsilon, where this factor accounts for clock drift. Basically, clocks on different machines can go at slightly different rates. And we use a factor of 0.2 here, which is quite generous for accounting for the clock drift. And this is how we get these 2 milliseconds, right? And note here that because we have such a fast network, we actually in our experiments never observe timeouts here. We still do take measurements just to be on the safe side. Okay, so this is how we implement log-free reads with a single RDMA and actually get very good performance, very good space utilization, sorry. So next I'm going just to briefly tell you that we also have a FaRM hash table. Right? We also have a key value store. This is one of the things that we built on top of FaRM. The reason why we opted for hash table is that it's a very important building block. But because we have this very nice programming abstraction, we were able to actually relatively simply try out different designs. And it's also possible to build different other data structures. Right? We also built a graph store, for instance. Our hash table is optimized for lookups and has a good space efficiency, which is important for main memory systems. It's a very interesting algorithm, but I don't have time to talk about it. So we can talk about it later, or you can take a look at the paper. So next I'm just going to briefly go through the results. So here I'm comparing a FaRM hash table, basically a key value store, to the TCP-based state-of-the-art key value store that will be running in today's data centers. This is a read-only workload with 16-byte keys and 32-byte values. Okay? And as you can see, the difference in throughput is really, really huge. We're basically able to achieve about 145 million operations per second with FaRM, which is almost a factor of 15 better than the TCP-based key value store. At the same time, the latency is also much better, basically 2 orders of magnitude in the latency at the peak throughput, right? FaRM lookups take about 35 microseconds, whereas TCP-based key value store lookups are about 10 milliseconds. So of course we can play with throughput latency here for the TCP key value store and reduce the latency by sacrificing some of the throughput. Still, we cannot really get close to FaRM. And with FaRM, there's no need to do anything like this. So we basically get great performance and great throughput at the same time. So we also implemented a graph store, basically modeled after Facebook's TAO graph store. Okay, this is basically, we implemented a read-dominated workload with 10 operations that are exposed by TAO. So these are basically simple operations used to traverse the Facebook graph. We implement nodes and edges as FaRM objects. Lookups are performed with log-free reads, and updates are performed using transactions. So we measure the performance and compare it to what was published by Facebook. And we are seeing basically a factor of 10 improvement in throughput. Again, and again, between a factor of 40 and 50 improvement in latency, which is even more significant in some cases. For instance, Facebook says that they cannot implement all the functionality they would like because of the high latency of their network. And with a system such as FaRM, basically, we could do much more. Okay, there are much more evaluation results in the paper. But just to sum up, I presented FaRM, which is a platform for distributed computing that keeps data in main memory, uses RDMA extensively. It exposes a shared address space abstraction and enables order of magnitude performance improvements. Thank you, and I'm happy to take questions.
Hi, Marcin Kowalski from EC2. The question I have is around if you've quantified why TCP specifically performs so poorly. Because it seems like RDMA network that you're using is inherently a lossless network. So
Yes.
TCP is designed to handle, much greater variety of things. So a more accurate comparison would be to use something like UDP if you know you're not going to have any loss.
Yes. So basically the reason is processing of the network stack. We also actually compared to UDP, and we were able to get slightly lower latency with UDP, right? And that was about the difference. It was still nowhere close to RDMA network.
And do you believe the difference is because of like in-kernel time?
Yes,
Or
yes, mostly yes.
Has there been any quantification in terms of what percentage?
No, we haven't actually done any comparisons like that. We just measured the CPU utilization and basically we were CPU bottleneck when running TCP microbenchmark.
Any other questions? Or if not, I will be forced to ask one myself. Oh no, here's one. Okay.
Hi, my name is Hein Melling. I wonder, is the next step across the data between data centers? Would that make sense?
No, because of the very high latencies, right? So there we cannot really avoid the speed of light constraints. So basically, there are several future directions that we were thinking about. So one is, for instance, looking into what kinds of primitives we should put into NICs network cards, basically to enable or to further improve performance or enable other functionality. Other directions for future work is actually implementing other interesting applications, seeing what we can do with this low latency, high throughput system.
So really great talk. You mentioned RAM Cloud. Can you say something about the difference between your work and RAM Cloud?
Yes. So the main difference is that actually RAM Cloud focuses on failure recovery, right? And they use basically the design of their system is really done so they can really quickly recover. So for instance, they keep the data in the log format even in main memory. And in our case, we're actually focusing on how to exploit these very fast RDMA primitives. So we can actually read data directly without interrupting the CPU on the other end. Whereas they cannot. They need the CPU to actually understand the log and traverse the log and fetch the data.
Well, I would just say that they're focusing on low latency, but as well as the recovery aspect. But anyway, okay,
yes, okay,
thanks.
Yes.
Jeff Risley from Brown. I noticed your evaluation sort of limited out at about 20 machines. I was just sort of curious if you could discuss how this sort of, or if this was a limitation, or if there was any...
Yes, the limitation was basically we have a cluster of 20 machines.
Sure. Do you have any ideas on how this would change?
We also ran everything on a cluster of 78 machines, with a slightly older hardware and everything worked. And basically, these InfiniBand clusters can scale up to hundreds of machines. Mm-hmm. So we would love to explore how far this scales. And yeah.
Wonderful. Thanks.
Hi, I'm Won from Cisco, and very nice talk. Thank you. I'm kind of new to the RDMA, so teach me. I'm actually asking wrong question. But my question is, the application point of view, if you have shared memory space, address space of big memory, right? So how do you manage that kind of data locality? Some application use if you have a global memory and then those are piece separate separate among all those machines, right? Yeah. And then one machine tends to use more kind of data from this machine, and then do you to migrate all those data between those?
No.
No?
No. Yeah. Basically, we rely on the application. We haven't done anything in this respect. So we basically rely on the application to allocate the data in the appropriate way, right? So what we do for the locality awareness, for instance, we enable the application to allocate the objects together, and then the system keeps them together even after failures and recoveries. But we actually do not. Another thing is that we expect basically one application to use the system, right? One large application, such as Facebook's Graph Store. So there is no tension between different machines. Basically, processes running different applications there.